Rates of change is the next application of derivatives topic. Real life situations where you're trying to find out how fast things are changing. So anytime you have an equation with respect to time, you can find a rate of change with that. So here we've got bacteria in a colony after T hours. We've got its equation. If we want to find its growth rate, how fast is it changing after 10 hours? In other words, how many bacteria per hour are happening at that moment? We would find first our derivative. And then at t equals 10, we'd get 75. And if we include our units as a rate of growth, this would be bacteria per hour. So what you could expect is from 10 to 11, that next hour you get 75 more bacteria. That would be the expectation. That's how much it is currently changing out at that precise moment. Then, show that the number of organisms will always increase. Well, we can show increasing and decreasing with our number line. If we were to graph this, we would show this with our number line. Now, what value would we put on that number line? Any critical point. So if I set my derivative equal to 0, I would get negative 15 over 6 as the only critical point. If we plug in numbers into our derivative before negative 15 over 6, plugging something in would be negative. So this part is decreasing on the graph. And above negative 15 over 6, like if you plugged in 0, you would get positive. But the important thing to think about here is we really only have to consider from time 0. So even though it was decreasing before negative 15 over 6, this equation would always be increasing because after time is 0, according to our graph, it's always increasing after that. Is that realistic? Can you have something that, like bacteria, can bacteria always increase? Or eventually they'll probably run out of food, run out of space. We have all of these things that this model might work for a while, and then it's going to fall apart because the bacteria is going to run out of food or the bacteria is going to run out of space. So is it realistic? Probably not. You gotta be a crazy scientist to have set this up. Mosquitoes in a controlled laboratory. What were they thinking? Controlled laboratory is called Winnipeg. So we've got a population equation here. T is measured in day. We want to find the growth rate. So anytime you're asked for a growth rate, that would be a derivative. So I'd find my derivative. Do we have any special derivative laws here? Yes. What rule? Product rule, chain rule, quotient rule, power rule. We would have chain rule, because that 0.09t is inside of E. So how do we do the chain rule? we do the derivative of our outside function. The outside function would be e to the 0.09 t, and the derivative of that is itself, and then we multiply by the derivative of the inside function, which is 0.09. After 5 days, we would just plug in 5 for t. Okay, to 3 sig figs, we would get 35.3. I rounded it to the nearest whole number because it's hard to see what a part of a mosquito would look like. So we have 35 mosquitoes per day. That isn't too bad. I mean, if I think about how mosquitoes normally are, if mosquitoes only grew at 35 mosquitoes per day, I think we could slap them under control. But I think they reproduce much faster than that. So what we're looking for in these questions as far as wording goes, anytime that they're looking for a rate of change, you know they're looking for a derivative. So here's a hot metal bar is placed into an environment where the temperature remains constant at 34 degrees. That is very warm. The model for temperature of the bar is 34 plus 90 e to the minus 0.2 t, where t is in minutes. So first of all, when I get a question like this, I like to play around with some of the ideas in my head. Like, how hot is this bar? Well, when t is 0, this would be e to the 0, which is 1, times 90, plus 34. So this bar is 124 degrees Celsius. Would not recommend touching that bar at that moment. Okay? Now, according to this formula as well, what kind of graph would this be? This is an e to the x graph with a negative in the exponent, so it would have a reflection over the y-axis. This is decreasing with a vertical shift up at 34. Exponential graphs have an asymptote, and this graph would have an asymptote.
Can't come back in like 10 times. 30?
Well, you can, but did you find him before?
Yeah.
Me? Times?
40 minutes? Can I come back in 40 minutes?
30 minutes? Whatever.
It's up to them. 40? 25. 25?
25. They would like to end early.
Okay. 25. Thank you. Thank you.
So if I think about this graphically as an exponential function, does it kind of make sense when you have something hot and you bring it into an environment that's cooler than that? Say you make yourself a cup of tea because you want to study IB math this evening, you like to drink tea while you study math. If you leave that tea out for a long time, eventually it will get close to room temperature. It will cool down. Life is nice that it's predictable that way. It would be very weird if things were unpredictable. Like today, I took a glass of tap water. 5 minutes later, it was white. Just by leaving it out in the environment. That would be weird. We like that our life is somewhat predictable. So it makes sense that this hot bar, if it was brought into a regular environment, would eventually get closer and closer and closer to the temperature of the environment. That makes sense. That is what this model is doing. Find the rate of change of the temperature of the bar 10 minutes after it was placed. So you brought this hot metal bar into the environment, you put it down, 10 minutes later, we're going to find out how fast it's cooling. So if we take the derivative, 34 will go away. We have a chain rule here. Whoops, almost. Got a little excited with the zeros there. There's our derivative. At 10 minutes, we plug that in, go to our calculator. There's degrees figs, my approximation signs. A negative sign there. So I can either, so there's a negative sign in my temperature, but when I'm writing a statement of this, can you see that I can include the negative sign by just using the word cooling? Because if temperature's going down, it's cooling. So it's cooling at a rate of, now here, some people would say, since I used the word cooling, I could put a positive number here. Some people like to include the negative number. I think it'd be fine. Is it minutes? And is our degrees Celsius? Yes. It's cooling at about 2.5 degrees per minute. If we wanted to figure out how hot it is at that moment, we could plug 10 back into the original equation and see whether or not this would be something we would want to touch yet. But whatever temperature it is at 10 minutes, we can expect in the next minute, it's going to go down another 2.5 degrees. All right, try this one on your own. All right, so check your derivative first. Did you get your derivative right? The derivative of the 20 will be 0, but then you have a product rule in the next part. And in the product rule, in the chain rule part, well, in the one part you have a chain rule as well. and try the last one. So part A, you would just plug into the actual equation. No derivative here because they're just asking for how much on a certain day. I thought I was getting this one.
All is life. And then you just do one of those. Bang. All right, guys, let's math it up here.
Part B is asking a rate of change. There you'd have to find your derivative. Again, you'd have a chain rule here. Derivative of the inside function is just 0.5. Plug in 5. And the rate of change is 104 deer per month. So what does that mean? Well, if we had 969 deer at the beginning of May, then we could expect that at the beginning of the next month, we would have 104 more. That would be the expectation. In reality, if we actually figure out what it is at the beginning of the next month, it might be off a little bit. What the derivative does is it gives us an estimate at how fast it's changing at that time and what to expect for the next time.